Good evening, everyone, and welcome to the Vacuum Transport Seminar. This is our 6th edition and also our last edition this semester. We have two interesting talks today, one organized by the side of the Institute of Hyperloop Technology. We will have Julian Gras talking about the parameter study on the effect of viscous boundary layers on the design limits for vacuum tube transport. And our second talk, organized by the Eurotube Foundation from Jens Adam. He's the lead of research and development at Furka, and he will talk about the aspects of polymer-based brake pads for linear braking of Hyperloop vehicles. We're very happy to welcome you tonight to our last edition of this semester. And at the same time, I would also would like to remember that we use this tool slido.com where the audience can post the questions during the talks. And then after every talk, we will go through those questions and have a quick interaction round with the speakers. Yes, so in that sense, thank you already very much for your contribution to the seminar. Also, thank you to the audience for attending today. And I would now like to hand over to Lucas from the Institute of Hyperloop Technology to give a short introduction about Julian, our first speaker. And exactly, I would hand over to you, Lucas.
Thank you very much. Yeah, I just got my headphones working at the right moment. Thanks for being here. I think, Julian, you can already start sharing your screen. In the meantime, I'm going to tell everybody that you are from Latin, where the TVE is located, the transit test facility. So you have the pleasure of basically every day imagining the new Hyperloop test facilities there. So that might be a really good thing. But then also for your studies, you've done your bachelor at the University of your bachelor in production engineering with a specialization on space science. Now your master's, and this is your master thesis now, on the influence of the boundary layer of aerodynamic performance of a ground-based vacuum transport vehicle, which I find very interesting. I've seen one of your previous talks already, and I think it's especially important for the pod length, but you will give us all the details about that. So I'm very, very happy to hear your talk. The stage is yours.
Okay, does anybody hear me?
Yes, we do.
Okay, and my presentation is for everybody.
Yes, we see that. Perfect.
Okay, perfect.
Thank you very much.
Okay, thank you for the introduction. Yes, as already said, my name is Julian Gras. I'm a student of the University of Bremen, and today I present you some results of my master thesis with the title Parameter Study on the Effect of Viscous Boundary Layers on the Design Limits for Vacuum Tube Transport Systems based on a simplified gas dynamical model. Before we start, why the introduction of Lucas? We do a collaboration between the TAM Institute of the University of Bremen, Center of Applied Space Technology and Microgravity, and the Institute of Hyperloop Technology with Professor Neu. So in the presentation, we first take a look at the technical and theoretical background. Afterwards, we come to a new design tool we created, and then I show you some results of the design tools, and at last we come to conclusions and some future work that can be done based on my thesis. So first of all, we have here artistic rendering of mask Hyperloop alpha white paper on the left side. On the right side, very generic schematic of a pod that has a velocity p and a diameter dp and a tube diameter dt. So I mean, it's clear for everybody. The main idea of the system is to provide a very thin atmosphere in order to drastically reduce aerodynamic drag and thus energy consumption The key point in order to obtain this is to decrease atmospheric pressure, for example, to what we assume 1 millibar. From an energy consumption point of view, a tube should be, of course, as small as possible because of energy consumption, maintenance, and. On the other hand, pods should be as large as possible in order to offer enough space for cargo or passengers. For that, we have two options. On the one hand, the pod diameter, but this quantity is limited due to the tube diameter. So the other option is to increase the pod's length. So why is it interesting to take a closer view on the gas dynamics in a VTT vacuum tube transport system? Why is it interesting to take a closer view on the gas dynamics there? Here, just a small overview. We have here an envelope of the relevant parameter space in terms of free stream Mach number and Reynolds number for pod scenario, and several input parameters we assumed, as well as for other typical means of transport. And what we can see is that our pod scenario operates in a very different atmosphere, in a very different environment, and that is mainly caused due to the low pressure which is in the Reynolds numbers. So we want to create a gas dynamical model. For that, we first need to do some simplifications to then adapt gas dynamical relations from scenarios that are already known. For that, simplifications are, for example, axisymmetric pockets that are coaxial with a tube. We use an inviscid flow and isentropic processes. That means reversible and adiabatic thermodynamical processes. We then can adapt gas dynamical relations from a Laval nozzle, here sketched in figure A. And when we then go to our pod scenario, we can see that we then have several similarities. On the left side, we can see that gas flows through a nozzle with a converging part and then a diverging part. And in the middle, where the smallest gap is, the throat is positioned here, denoted with number 3. And then we can go to our pod scenario, and instead of using a pod velocity, we can switch to a reference frame that is co-moving with the pod, so that the air in the tube walls pass the pod, which is a common method in flow dynamics. So on the right side, we can see, okay, the flow flows through the tube, and when it passes the pod, the gap between pod and tube narrows and widens up behind the pod again. Okay, when we adapt the relations of the Laval nozzle, what happens to the gas dynamics in detail? When we take a look on the gray solid line, we can say, okay, when we increase the gap size, as I already said, for example, from position 1 to position 3, we can see on the x-axis that the local Mach number increases. So on the other side, local thermodynamics, for example, pressure and temperature and density decrease. And behind the pod, the quantities recover to their undisturbed conditions at position 1, that is denoted with a subscript with the infinity symbol. And so we have here similarities between both Laval nozzle and pod scenario, so that we can adapt the relations. In addition, we have this equation that is already known, that is also already known from the Laval nozzle. The equation shows the combinations of blockage ratio and pod speeds, where in the smallest gap, I recall it's position 3 in the constant body section area, where the local Mach number is exactly 1. So we have a local velocity of the speed of sound. If we by plotting this curve, we obtain the curve that most of you have already seen, and it's denoted as the isentropic limit from a gas dynamical point of view, because at this particular point, the maximum mass flux of the system is reached. If we exceed this limit, for example, by increasing the pod diameter or increasing the pod speed, we've already heard last week that we generating shock waves, high pressure region in front of the pod, and several other effects. So for us, we say our maximum limit or upper limit in our scenarios is that we locally reach maximum Mach number 1. Okay, next, as my title of the master thesis says, we want to see what does the boundary layer effect on the gas dynamics do. So in general, in finite distance to a wall, a flow can be determined by the state variables and gas dynamics I point out above. However, due to internal friction, the flow develops a thin viscous layer in close vicinity to a wall, and the viscosity takes over the velocity transition from the undisturbed free stream to 0 directly at the wall, as sketched in figure A. So the most interesting quantity for a boundary or in a boundary layer theory is its thickness, and for that, several concepts of defining the thickness exist. For example, the delta theory and the delta 1 theory. Delta 1 is the displacement thickness, and the main property of the displacement thickness is that from a gas dynamical point of view, it pushes the inviscid outer flow away by its thickness. So if we just take a look on an on-streamed flat plate, the displacement thickness adds an effective height on top of the wall. So, as well as for the gas dynamics, we use several simplifications in order to determine the development of the boundary layer. Here we use the relations on-streamed two-dimensional flat plate, which is typically used for describing the boundary layer development for means of transport. In the figure, you can see that due to the Reynolds number I already mentioned, and is mentioned in the equations below, due to the Reynolds number and the viscosity and the low pressure in our system, we have a completely different displacement thickness development compared to the developments on other means of transport. Here we can see, for example, using a pod length of 50 meters and a low pod velocity of 80 meters, we have a displacement thickness of around 30 centimeters on top of the pod. So if we have an effective height on top of the on pod and then consider our gas dynamics, we want to investigate how does the boundary layer development affect the gas dynamics of a VTD system, how does the design parameter limits are shifted, and last, how does a variation of the ambient pressure of the undisturbed pressure affects our design parameter limits. So let's put all together in one design tool. We first have our inputs that are the blockage ratio. We've chosen different pod diameters and Mach numbers. Then we use a laminar and turbulent model for the displacement thickness development. And then we first generate a geometry of our pod and of our system, determine local gas dynamics with the relations of a Laval nozzle, and then we determine the local boundary layer. And then on top of the nominal geometry, we put our displacement thickness and obtain effective pod diameter, and then recalculate the whole process until tolerance is crossed. And then when we've reached when we've calculated all calculations with our input variables, we have as an output all local quantities for all input variables we used for the blockage ratio, Mach number, and pod length. Okay, first of all, let's take a look how does the displacement thickness development changes when we consider gas dynamics of the system. First of all, the solid line are the results when we only use on-streamed flat plate relations. The dashed and dotted curves are if we consider the gas dynamics in our narrowed gap between pod and tube. We can see that we use on the left side a laminar model and a Mach number of 0.07. We have a decreasing displacement thickness development when we increase the blockage ratio, and on the blue curves we can see that when we increase also the Mach number, the local displacement thickness development also decreases. On the right side, we have the results when we use the turbulent model. Okay, as I already said, the displacement thickness adds an effective height. So we put our effective part on top of the blockage ratio and obtain the results here shown in this figure. We can see if we completely ignore a boundary layer development, we have, for example, on the left side, the blue solid line with a displacement thickness, a blockage ratio of 0.51. And when we consider the displacement thickness development, we have an effective height that increases our effective blockage ratio. On the right side, we can see an interesting effect. We can see that the curves here ends at a certain point, and at this particular point, the effective part of the of our blockage ratio leads to an exceed of the isentropic limit. So if we use here a Mach number of 0.27 and a blockage ratio of 0.51, we only can use, for example, pod lengths up to 10 meters, and then we obtain local Mach numbers that are higher than 1, and that's the point where our simulation stops. Okay, so this is an interesting point. Let's take a closer look on this area where we almost reach the speed of sound. And here we can see that, for example, we use on the left-hand side a small blockage ratio of 0.09 and high Mach numbers of pod speed, for example, of 0.65. We can see, okay, if we don't consider the displacement thickness development, nothing happens. However, if we use our boundary layer effect, with increasing pod length on the x-axis, we can see that with increasing pod length, the local Mach number between pod and tube exponentially increases, and at a certain point, depending on a turbulent or laminar boundary layer model, we can see that we use or can only use pod lengths up to 30 meters or up to 50 meters. As I said, we only consider local velocities that are at maximum of a local Mach number of 1. And here we have curves that end before we reach this value. And this is caused by a too large step size of our input variables, and is just a calculation issue. So as next, let's see what happens to our design parameter limits. The black curve on both figures, do you already know? It's isentropic limit, or for most of people of you already know that as Cantrobit's limit, but I will say here as I would denote it as isentropic limit. And we can see here at on the orange and on the blue curve, with increasing pod length and due to the displacement thickness, the isentropic limit shifts and lowers all values. For example, using Mach number of, for example, Mach number 0.1, and don't consider the displacement thickness, we can use blockage ratios up to 0.85. But considering, for example, a laminar model on the left-hand side and a pod length of 50 meters, we only can use a blockage ratio of 0.7. So this is an interesting fact from a gas dynamical point of view, that the displacement thickness shifts the isentropic limit curves this so far. So let's take a closer look on how does the relative deviation does look like from the blockage ratio and on the Mach number. So relative deviation gives us a percentage on how our model differs from the only gas dynamical solution. And we can see here that on the left side, the relative deviation of the blockage ratio decreases with increasing Mach number and with increasing pod length. We can also see here that using a turbulent model and low pod lengths, for example 4 meters, we obtain lower relative deviations than using a laminar model. On the other side, at large pod lengths, we can see that a laminar model results to lower relative deviations. And several effects can we see on the right-hand side. We can also see that maximum relative deviations on the left-hand side are reached up to 40% about, and on the right-hand side up to 60%. So when we consider the displacement thickness in our turbulent boundary layer model, we have to decrease our pod speed, for example, about 60% if our pod is about 50 meters long. And that is a very high value. So yes, before we continue, this is an interesting area as it shows two competing effects. We can see that the relative deviation first decreases with increasing Mach number. This comes due to the fact that at very low velocities, the displacement thickness is very, very high. And with increasing Mach number, it decreases. But on the other side, we know from the slide before that in general, with increasing Mach number, the isentropic limit decreases. So we have here competing effects, and we see it later again. So let's a closer view on how does our blockage ratio needs to be reduced along a pod length from up to 50 meters for several given pod speeds. And we can see what we have already seen, or what the slide before indicates. We can see that with increasing Mach number and with increasing pod length, the nominal blockage ratio needs to be reduced in order to not exceed the isentropic limit. In addition, we have pictured here the relative deviations again, and on the left-hand side we can see that the orange curve, as I already said with the competing effects, that the orange curve with a low pod speed causes higher relative deviation compared to, for example, pod speeds with a Mach number of 0.19. Interesting to see is also that it only occurs on the left-hand side when we use a laminar turbulent model. On the right-hand side, it is not really visible. Okay, then last, let's see how does the pod speed changes with increasing pod length for given blockage ratios. And already as denoted, as shown slides above, with increasing pod length, the pod speed must be reduced in order to not exceed the isentropic limit. And again, here we have at very low, no, on the other side, at very high blockage ratios and very low Mach numbers, very high relative deviations of the pod speed. So as a summarize, we have here a 3D plot that it shows on the left-hand side our laminar model and on the right side our turbulent model, how our parameter space of blockage ratio, pod speeds, and pod length decrease or changes with increasing pod length. Yes, as a third objective, let's take a short view. What does the tube pressure in general affect on the design parameter limits? And we can see here, if we use higher tube pressures, for example, 10 millibar or 100 millibar, we can see that we come closer to the only gas dynamical solution. But if we decrease the tube pressure further to, for example, 0.1 millibar, we have drastically reduced blockage ratio and Mach number in order to not exceed the isentropic limit. On the right-hand side, we can see the results with a turbulent model, and we can see that for the used pod length of 50 meters, the design parameter limits do not shift so far as pictured on figure A. As last, we can see here the relative deviations of the blockage ratio, and as the slide before indicates, it's with decreasing tube pressure, we have to drastically reduced design parameter limits. On the left side, laminar model a little bit more than on the right side, turbulent model. Okay, let's summarize the results. We first can say the effect of the boundary layer on the gas dynamics increases with the pod length. We've seen that the design parameter limits of the blockage ratio and Mach number decrease up to 61% when taking the displacement thickness into account. And we have seen competing effects that show that we have higher loss at low velocities than moderate pod velocities. We've seen that with increasing tube pressure, the design parameter limits of blockage ratio and Mach number decrease to more than up to 81%. So for a boundary layer point of view, higher tube pressures favors the system. We have less loss in design parameter limits, but if we keep in mind the key point of our tube system, of our VTT system, that we want to reduce aerodynamic drag, these both sizes come in conflict. So as an outlook for future work, we can use more accurate relations. For example, for the boundary layer, we used in our work here separate views on laminar turbulent models. As next step, maybe a laminar turbulent transition would be interesting, axisymmetric and three-dimensional boundary layers, and not flat plate relations as we did. For the gas dynamics, non-axisymmetric pods that are coaxial with the tube are interesting. As you know, they are driven on tracks. What happens with the boundary layer effect if we exceed the isentropic limit? And from aeronautical engineering, it is known that you can control a boundary layer, for example, by using a compressor and bypassing air through the pod, which would decrease the boundary layer and then favors the parameter design limits of the system. On the other hand, we've seen that for low pod lengths, or for short pods, that the turbulent model leads to better results. So boundary layer control regarding triggering the boundary layer to transit to turbulent is also an interesting point. And last, of course, CFD simulations for comparing my results with with CFD simulations are interesting, and of course physical experiments would be also interesting, of course. Yes, that's it from my side. I think.
Thank you very much. We have a few questions, but we'll just pick two to get done quickly here because the next speaker is waiting. So the first question what's the most important simplification that you made for the model?
I would say the most important simplifications is that we used only two-dimensional flat plate relations. I mean, for our calculations, we assumed that our pod is just a surface that is driving through the tube. And of course, as a next step, it would be, of course, interesting. How does it change if we have something like a cylinder or a capsule? Or yes, I mean, this is a two-dimensional
simulation. Yeah, I think we've seen that for magnetics as well, where two-dimensional simulations or three-dimensional simulations can vary a lot, but interesting simplification. Yeah. Then the second question is there, and that's relating to a test facility now, so that you get the question right. Is there some value that the boundary layers approach? Oh, no, sorry, that's not the, there was another question. Damn it. Okay, that's not one. But I think it was something like, what's the important thing when you do a 2-to-1 scale of a test facility? So where the test facility is just half of the size, what's the importance there? What do you want to look at there?
On half of the size, I mean, it's a little bit hard to say. I mean, on the one side, on the scale, I'll go back. As it shows here on the left side, we can see that I considered blockage ratios from 0.09 to 0.94, so almost from 0 to 1. But the most important size here that I want to show you is that we have to consider the pod length. I mean, I've just assumed here a maximum pod length of 50 meters. I mean, I think it's more interesting to know what happens if we increase the size to about 100 meters. I cannot really say what happens if we decrease or to scale it to half or twice its size. It's hard to say.
It's probably not that important, right? Because that size doesn't matter for you. It's the length of the pod that matters for you. Yeah, great. Thank you very much for your presentation. And then I would like to hand over for the next presenter.
Thank you.
Yes, I would say we can hand over quite right away to Daniel to give a short introduction about Jens Adam, the lead of research and development of Foucault-Reitbeläge. Thank you, Daniel.
Thanks, Natalie. In the following, we have the pleasure to attend one very interesting topic about the aspects of polymer-based braking pads, which are following us mainly in each of the vehicles for Hyperloop we are developing, not only for the primary braking system, but also for emergency braking system concepts. Jens Adam has a very vast experience in characterization, quality control, optimization of ceramic materials. And since 2022, he has been working at Furka and helping out quite intensively in the efforts in promoting research in Hyperloop teams such as Swiss Loop or EPFL Loop. Currently, we are working out a research partnership to validate some of our technologies on the vehicle side. So I would really like to hand over now to Jens, and really looking forward to the presentation.
Okay, thank you. So I go to share as well. A moment.
Great, we see the screen.
Yes. Now you see the entire slide?
We can see it. We can see it.
Okay, great. So thank you for inviting me and for introducing me. You mentioned the title. So we have the cooperation of or concerning the brakes. And to introduce also our company and what we are doing, we are the only company in Switzerland which develops, manufactures and sells those friction materials. And in Breitenbach, Canton Solothurn, we produce these resin bonded friction linings only. Among our customers, they have the following applications. So friction linings are in most cases brake pads for trains, trams, special vehicles, cable cars in the mountains, elevators, and so on. But we are also producing clutch linings and sliding or slide linings. Before, asbestos was an ideal material in the use in those resin bonded brake pads, but its production and use was banned, for example, in Switzerland in 1990. And the following categories emerged. These are non-asbestos organics or just organic resin bonded brake pads. Then you have the two categories with, for example, steel fibers called low metallic or semi-metallic. And we are producing these NaO and low metallic categories. At the moment, we offer around 50 materials, and each of them contain 10 up to 30 components from more than 100 raw materials. Other material concepts in friction braking are sintered brake pads, where you use sintered metals with a high fraction of graphite. We also can offer those. And there are these full ceramic brakes where also the disc is made of ceramics. So why I use the term linear braking is that you are using this tube and you have to brake on a rail. On the bottom image, you can see a test of Swiss loop where you can see this double T-beam rail. And if you look at the entire pod, we have the, do you see this, the arrow as well?
Yes, we see it.
You have the small brake system as a, maybe for you not so important or interesting part, as you have this interesting gas dynamics and magnetic levitation. But it's also important. And here you have it more in detail. And if we look from down under up here, you have this image. So here, this construction embraces or surrounds the upper T shape of the beam. And we have the caliper, and the reddish material, for example, is our brake pads from our company. So these were the photo were taken after the test in European Hyperloop Week last year. We have the following contacts to groups working on that. We are sponsoring pads to Swiss Loop, to Shift Hyperloop in Norway, and some years ago to APFL Loop. And now I'm taking care for the teams of Swiss Loop, and since 1 year before for Shift Hyperloop. And so when we started each discussion with a new team, they surely want to know a coefficient of friction for their calculation. And then, we surely discussed the aspect of braking on a rail. Up to last year, it was an aluminum rail. And they, for example, the Norwegian team didn't want to scratch it very strongly. We discussed if pads can stand dislocation or even gaps between the rail sections. And in our focus, it's always, we are looking for the factors resulting in braking energy or power per pad area, as this is a measure for thermal load. So what are the results with these projects? This is summarized on this slide. The brakes and brake pads worked well, and no problems were reported. So, and now, you can ask, is everything said about these friction brakes in Hyperloop vehicles? It's my opinion that we all need to know more, because surely requirements will become more demanding. And so I go on to the second part. On the first side, the coefficient of friction is a simple physical value. We have just this relation of two forces. It's the friction force, for example, of a sliding block on a plane, divided by the normal force. And on this equation, you can see that it doesn't depend on the friction area. So in the example of the sketch, if the blocks have the same mass, the same friction coefficients will result. And further on, it has a very small range of values. If you look at this range, this is applying for our brake linings. So they are starting somewhere around 0.2, going up to 0.65, for example, and everything is happening in this range. Then we have lower values down to nearly 0, for example, by our slide linings. Then it's sometimes people are not aware the mu can be larger than 1. There's an example of sliding aluminum on dry and clean aluminum, but there will be no other magnitudes like in the other example I'm giving here. This is also extreme. You have for electrical resistivity as an example, very much orders of magnitudes in the difference in comparison to the coefficient of friction. And now in friction braking, it depends on many things. Here I list some mechanical and structural factors. The really, I think, very important is the adhesion, depending on the friction material and the counter material, but also roughness. You have mechanical locking of peaks which are in contact. And also you get those peaks if you have hard materials in the counter material, for example, in metals. And these together results in run-in processes which are time depending. The same is for flatness and homogeneity of the pressure in the contact area. There will also be a run-in process in the contacts, depending on the brake shoes and their stiffness, for example. Then it's depending on the velocity. And we also have a static case, as I will show. And then a microstructure of the brake materials with many phases having adhering, abrasive, or lubricating functions. And then in the contact, there may be residual solid state lubricants from the pads, but also water, oil, salt, rust, or dirt of any kind. And as we observed, noises, vibration, or brake judder also influences the level of the friction coefficient. And now I list some thermal and chemical factors. You have the friction heat generation resulting in temperatures increasing in the pad and in the disc. Here it depends on the friction energy, and there you find, if you look at the normal forces or clamping forces or pad or contact pressures, you have the product of the friction coefficient of the pad pressure or contact pressure, the pad size, the relative velocity, and the braking time. And then on the other side, it depends on heat flows into the disc, and so on the mass of the disc. A smaller amount will flow into the pad, and then you have a ventilation. Now the following mechanisms are influencing mu at high temperatures. It's softening, weakening, up to decomposition of the polymers. So this is known as and experienced as fading if you reach high temperatures, and it is also influencing the wear. Then we use desired chemical reactions, for example, anti-fading by decomposition of sulfates. There are also thermal effects at very high temperatures in the disc, for example, like arching, distortion, and so on. And here, via these mechanisms, mu effectively depends on the pad size. Then there is also formation and wear of desired tribo layers or even thermally damaged layers between disc and the pad material. And this is depending on all these factors, including, for example, acceleration of a vehicle. If you look for emitted particles and their analysis, you can see acceleration or opening and closing of the brakes, for example. So there is no simple value for the coefficient of friction. And here I want to start with an example from a standard. This is a standard of the Society of Automotive Engineers, called, in most times, it's called ACAR Master Test or J2522. It's just an example I want to show. This standard is given these diagrams as an example how results from this test can be displayed. You can see, for example, here, and just for example, the sections 9 up to 15. In section 9, you have a fading test with strong increase in temperature, which is displayed here. And here you see a clear fading effect and a strong variation of mu. And that's also can be said about pressure sensitivity, temperature sensitivity. So they try everything that may happen for cars, for example, in this case. This is a test for cars. Due to technical reasons, we cannot perform the ACAR master test at Furka, but we do similar things with our braking test bench. For example, here you see a series of varying the contact pressure from 40 up to 100 Newton per centimeter. And here we have displayed the effect of 10 brakings of 4.5 seconds. And you see slight fading as well. You see stronger fading when you go to the higher pressure, resulting in a lower coefficient of friction and resulting in higher temperatures at this higher pressure. And to make it comparable or to give a image or estimation about it, you usually have to give very detailed conditions, as I do here. And I want to state that in this case, the temperatures, you see these series of 10 braking events start around 80 or 100 degrees C. And by 10 braking it's increased above 250 degrees C. But this is a temperature we measured on the middle of the disc jacket. So much higher temperatures can be expected in the direct contact. And then we also have cases of linear braking. To look at this, we use a mechanical testing machine. And here you see a metal plate. Here you have two pistons with hydraulic forces can be applied. We put the samples here, and the pistons clamp the samples with contact to this metal plate. And then machine is pulling, and we can calculate a quasi-static mu, or which is related to the breakaway force, for example. This is interesting for the application of elevators. On the right side, you can see the top of an elevator cabin, which is with a brake, braking on this rail. And it's used to fix the cabin when the floor level is reached. And additionally, it's emergency brake. But the more important case is just the static case on this rail. And to give two more examples, we have this material F9158, which is optimized for highly dynamic conditions and showing higher coefficient of friction. But when we take the breakaway force and the related mu, it is very low. And for this material, it's the other way around. It is very weak in fading stability, but it has a very high friction coefficient for the static case. So first conclusions are the mu depends on mechanical, structural, thermal, and chemical factors. And so it depends on the application, the operation parameters, and the current and previous braking conditions. And that's the problem very often, as it is generally impossible to precisely predict the friction behavior or even an average value of mu of brake pads in a completely new case. But we have many experiences with this. And so based on this, we usually are able to recommend suitable materials. But very often experiments comparing some materials are needed. So from our point of view in the applications, we have as usual cases braking on discs, drums, axles, and the pads have many friction passages on a small area, for example, of a disc, and high temperatures are emerging. And then we have these braking on rail cases with usually low velocities and low friction heat. And in Hyperloop vehicles, this is a new case for us, because we have this high-speed braking on rails, and we have to discuss the materials of the rails, the roughness, the straightness, also the aspect of gaps, for example, when you are going to construct switches. And as another consequence of braking on rails, you have only one passage of the pad materials or of the brakes on a longer rail section per braking, and so the rail doesn't get hot. I'm not sure if this is an advantage because of better cooling of the pad, or if we see also different behavior because of these run-in processes and trivo reactions, trivo layers. So this has been tried as well. And then Eurotube mentioned potential requirements concerning the vacuum system, and that may aim at particulate wear, which is unavoidable, but it can be designed if it is coming more from the pad or more from the rail, for example. And also degassing from the pads is a reality where we can look at, and then it would be the first case, for example, if you would have to minimize it. And then just as a remark, when you have heavy vehicles and high speed, as in trains, friction braking will not be the only brake, as you have in trains, for example, recuperation, eddy current, or magnetic brakes, as those materials in friction brakes cannot stand all the energy from braking large or heavy vehicles with high kinetic energy. So the last conclusions are as follows. Our materials worked in those small Hyperloop test pods. They were suitable for the occurring braking power and conditions concerning the coefficient of friction, the pad pressures, the pad sizes, and the velocity, and with mechanical properties which are related to this. That's most important one is internal shear strength. But I think, yeah, we can expect that your requirements will become tougher and more complex. And so for an optimization, we need to know more about properties of our materials in this application and the conditions. So it would be interesting to measure the degree of wear per braking energy, the real mu from a real deceleration data, and the temperatures, which, for example, could be measured at the carrier plate or within the pads. And we also should compare different materials which are, for example, differing in hardness. That will be done by Shift Hyperloop this season. And then we can start to use materials which differ in various aspects, or go and use special functional components and so on. So that's my hint, or what I want to say. So please, you have very interesting projects, but also plan the brake experiments with those materials and collect and report respective data. We are very interested in discussing this and going further with possible optimizations if when they are needed. So thank you very much.
Thank you very much, Ed, for the nice presentation. I think that's a very good point. Since all we all know, without brakes, we couldn't be able to to stop the vehicle of crashing. With this, I would then jump straight into the questions. We have quite of them. So the first one would be, how much did the requirements of the braking pads change among the teams, the student teams, when considering that the I-beam material and shape has been the same for the competitions? Now, in this case, the years where student teams such as Swiss Loop or EPFL Loop have participated in Los Angeles.
For my groups, I think it was a large issue with this aluminium beam. So we tried to use very low steel or metal, and also to use low contents of abrasive particles like ceramics. And then Swiss Loop this season, they didn't ask much for requirements.
Okay.
And as I showed on these examples, it would be nearly impossible to predict what will happen with the same pod and with the same brake if you just change the beam, or the rail, as you have all these roughness aspects and so on, and yeah, so
the requirements are always different.
Right, and it's said that we don't have wear data so far, but I think it would be more depending on roughness than on the material itself of the beam.
This will lead us to the next question. Someone is asking if there is any possibility to certify such braking pad materials for Hyperloop industry or applications. Do you work with a certification entity in this regard?
I think we have particular certifications with the customers, but we do not have those general certifications, for example, from rail industry. And I'm not aware about specific certifications in the case of Hyperloop technologies. So if they are emerging, we have to look for them, what can be done. But so far, no certifications. And as I learned from some videos about your technology, I think certification is a large topic for many aspects.
Yeah, exactly.
Like the security or safety of these vacuum capsules for transportation of persons. So
yeah, exactly.
do you know that it is already existing?
For now, as far as I'm concerned, there is not an official entity which is targeting the certification of Hyperloop technologies. But as you mentioned, this is something everyone is now looking into in case a potential then test track is or commercial route is then implemented.
So, yeah, so I think we could learn from those examples like Arca Master, and yeah, transfer it to the lower amount and of brakings which are more similar to each other in comparison to driving a car through mountains or on the highway and so on.
Exactly. This will lead us to the last question then. Someone is asking, do you have information about sudden gaps and misalignments of the track with respect to testing of the brake pads? How do they behave?
Yeah, so we expected that it could be really destructive for the pads. And for example, so the reddish pads you could see on the picture, they are high in rubber content, and we hope that yeah, they could stand it and it looked good. You have clear traces of the contact, and I think also traces of maybe the contact which is lifting off material at those gaps. But this season, we also will have harder materials with which potentially will have lower wear. And I think Swissloop, they turn to select the material of the rail, but I don't know if they could connect everything and will further on have gaps or not.
Perfect. Then thank you very much for answering the questions. I think now we are also done with the talks. Natalie, and over to you.
Yes, exactly. So again, thank you very much to our talks today, to Julian Grass and to Jens Adam from Fuggerijbelegge. It was very interesting, both of the insights and the new things that we learned about your field of studies or work in that regard. And thank you very much for the contribution to the seminar. At the same time, also thank you very much to the audience for attending today, as well as throughout the semester, for your participation with all the questions. It's always very nice to have those interaction rounds, and which is basically the goal of our seminar here, to provide a platform on Hyperloop with the involved companies or organizations in Europe in the Hyperloop sector, that we provide a platform where we can host those presentations and the interactions, and to promote the exchange on that. So in that sense, thank you very much to everyone who participated in this semester. So this was the 5th semester that we're doing this seminar. We started in 2020 in March, no, in February, end of February, I think. And we plan to continue it as of next semester. The reason why we always only have around 5 or 6 editions is that we're from different universities, and the semester period is overlapping in just a very short period. So in Switzerland, we start the semester quite early in February, and in Germany it's later. And in Switzerland, we end the semester earlier as a consequence. So this is why our seminars last for usually around 6, maybe 7 editions. And as soon as we will have the new schedule, we will post it online, and we would be very happy to welcome you all again next semester, more or less around end of October, when we will start again. Exactly. So I would also like to thank again the organizations that are part of our seminar. So it's Daniel from the YouTube Foundation, Lucas from the Institute of Hyperloop Technology, Elias from TUM Hyperloop, and Pia from Zero Hyperloop, and me, Natalie, I'm from Swissloop. I'm representing our Hyperloop team from Zurich.
Well, for that, thanks a lot for the nice moderations you've done for all these sessions. I didn't realize it was 5 semesters now, but thanks very much, yes. Natalie. I think that's very, very great. Thanks for all the behind-the-scenes organization that you are doing. That's really good. I'm also looking forward to seeing all of you next time. The schedule will be on LinkedIn again. We'll put the events up. We'll put the links, the sessions up. And I really see that a lot of sessions are also now watched on YouTube a lot by, I've recommended them to a few experts in JTC20 and so on. So if you want to look up special topics, that's the resource to do. And that's why I like the seminar.
Thank you very much, Lucas. And as I said, I mean, it would not be possible without the collaboration of everyone. And exactly, so I'm looking forward to the next semester, the next edition. I think we all do. We're all eager for the next talks. And yes, exactly. So we will post our new schedule and the new dates as soon as possible on the website when we have the dates for the semester and so on. Our YouTube channel that Lucas mentioned provides all the past recordings. So there one can have a look at the previous talks. Yes, exactly. And so in that sense, we wish everyone a nice summer, nice time until we start the seminar again. If somebody has questions to any one of us, do not hesitate to reach out to us. Usually we find all of our email addresses online from our organizations. And yes, so I would like to thank everyone again for this semester, for this seminar, and wish you a good time and see you soon. Have a good time. Goodbye, everyone.